All right, everyone, we're going to get started. I'd like to introduce A. Jesse Jiryu Davis. We are going to grok the GIL.
I'd been programming Python for a number of years and kind of thought that I understood how multitasking worked. I understood how it worked in Java and C, and I kind of lazily expected that the same principles were applicable to Python. I didn't really understand how multi-threading worked in Python particularly until I started working for MongoDB. And once I got there, we were writing the kind of complicated, high-performance Python that required me to really understand how multi-threaded Python specifically works. And in order to do that, I finally really had to understand the GIL. So who here has heard of the global interpreter lock? Please? Yeah. Who here has seen the global interpreter lock? So almost everybody here is in the same position that I was in then. Let's be curious. Let's look at it. So I've got Python 2.7 checked out of GitHub here in my editor. I'm using Python 2 rather than 3 because the code that we want to look at is simpler in Python 2, but everything that we're going to talk about today will be equally applicable to Python 3. Let's go find the GIL. It's going to be in a file called ceval.c. And what this file contains is all of the logic that's at the core of the interpreter, where it actually, as Guido says, executes compiled code. And like any respectable old software project, it's also got a 20-year-old to-do at the top, which has long since been done, but we forgot to delete the comment. The GIL is in here somewhere, so let's find it. Once the GIL was famous, Guido added this helpful comment around 2003, but the GIL has been here since the early 1990s, since he first wrote a multi-threaded Python interpreter. The global interpreter's lock's name is interpreter lock. Its type is pythread type lock, and that's just an alias for whatever is the most basic lock on your system. On Unix, this is a mutex, a mutual exclusion lock. It means that when one thread grabs it, no other thread can have it until the thread that is holding it drops it. On Windows, it's something else with the same behavior. We can see that it's static, which means that there is only one of them for the entire interpreter process. It is truly global. The other thing that we can see here is that it's initialized at the very beginning of the interpreter startup. The main thread calls this function pyeval_init threads, allocates some lock. It's going to be a mutex on Unix. On Windows, it's something else. And the other interesting thing to see here is that as soon as the main thread has created the GIL, it locks it. The GIL is born locked by the main thread. The mutex is a lock that threads have to hold whenever they're executing Python code. And this leads us to a principle about how the GIL affects our multi-threaded programs that's simple enough that you could write it on one hand. One thread runs Python while n others sleep or await I/O. And if that's a little hard to read like that, then we can see it like this again. You can have a truly multi-threaded Python program. All of your other threads can be doing other things. They can sleep, they can establish network connections. The only thing that two threads can't do at once in Python is run Python. Now, this principle is simple enough to write on your hand, but it might take a little bit of work to really wrap your head around what this means for your programs. I like to think of my Python programs like an old mainframe computer. This is a PDP-6. It's a mainframe from the late 1960s. It was one of the first to implement this idea of time slicing. Even though this mainframe only has one processor, it could simulate parallel execution by rapidly swapping off among various tasks. So even though it only does one thing at a time, it appears to be doing multiple things at a time. Your Python programs running in CPython act the same way. And over the years, there have been many attempts. Like, why did Guido implement it this way? First of all, it was simple, and it's very fast for single-threaded execution. And in the early 1990s, multi-core computers were less widespread than they are now. There have been many attempts in the years since to work around this, to get truly parallel Python. There's Jython, which is based on the JVM. It's free-threaded, but it's got a lot of incompatibilities with CPython. There's a research project in PyPy to remove the GIL from PyPy. And over in the next room, Larry Hastings is giving us an update on his GILectomy, his surgical removal of the GIL from standard CPython. And so over in that room are a bunch of idealists. People who want to know what the future might look like. And you and I are practical. We want to know, how do we write fast and thread-safe Python with CPython today? Now, Python has two kinds of multitasking in it: cooperative and preemptive. Cooperative multitasking is where a thread is running along executing Python, and at some point it does something that it knows might take a while, like establish a connection. Since it doesn't need to run any more Python for a little while, it drops the GIL voluntarily so that other threads can run Python while this thread does something else. The other kind of multitasking, which is also implemented in CPython, is preemptive multitasking. That happens when a thread's been running and using the GIL for a certain period of time, and the interpreter decides that it's had the GIL long enough, and it grabs the GIL away from the thread and forces it to drop the GIL so that some other thread can run Python instead. This is like what I hope you learned when you were a toddler, that if you're sitting on the swing and then you're done swinging, you don't just kind of sit grumpily on that swing for the rest of recess so no other kid can use it. You get up and you go do something else, and other kids can use the swing set. So cooperative multitasking is when you get up and you leave the swing set behind. This little girl is ripe for preemptive multitasking, which is that the interpreter is going to take the GIL away from her after she's used it. This happens every 1,000 bytecodes in Python 2, and then in Python 3, Antoine Pitrou rewrote the whole thing to be much better, and now it's 15 milliseconds. But you don't really have to worry about that distinction when you're writing your code. We're going to look at examples of both of these. First, we're going to look at an example of cooperative multitasking, where I'm going to start two threads, and on each of those threads, I'll establish a network connection. And we're going to see that because cooperative multitasking works, each of them can wait at the same time for that connection to be established, and then they'll both resume once that's happened. So I've written you a little program here. And since we're going to do network stuff with threads, we import socket and threading. And then I'm going to make a list of messages here where I'll just use this to record what the program does at every step. Then I've got a function here called doConnect, which creates a socket, and it records that it started to connect, and then it connects to python.org on port 80. And then it's going to write that it has finished connecting. Now, we're going to start 2 threads, and each of them will execute this doConnect function. We start both threads, and then we call join on both threads, which makes the main thread wait until both threads have finished, and then we're going to print out the list of messages that they've recorded. So the question here is, are we going to see that one thread completes all of its work before the other thread can start, or are we going to see some sort of interleaving, some cooperation between them? Let's find out. So that's interesting, right? We see connecting, connecting, connected, connected. What does that tell you? That tells you that when the first thread reached this spot, it dropped the GIL. And that allowed the other thread to also start up, execute enough Python to also reach that spot, and then also drop the GIL, and then they completed in some order or another. So how is this actually possible? How does the interpreter allow threads to cooperate in this way? Let's take a look. So when you call import socket, the logic that you're bringing into your program is all implemented in C in a file here called socketmodule.c. And the particular function that we're interested in here is sockconnect, which is the socket.connect function in Python. And this is all in C, and it takes a couple of arguments. The socket object, which is like self, and the address that it's going to connect to. And it needs to do a little bit of work to convert that Python tuple into a standard C address thing. And if that works, then it does these 3 lines. And this is really important. That PyBegin allow threads macro, that's where this thread drops the GIL. Because on the next line, it's going to call internal connect. And that'll do something or other, but it's all purely in C. It establishes that connection using pure thread-safe C and does not touch the interpreter at all. Then once that work is completed, it calls py-end-allow threads and reacquires the GIL before it touches the interpreter again. Now, if there are no other threads competing for the GIL, then py-end-allow threads will allow to immediately reacquire the GIL and continue. If there are other threads that are competing for the GIL, like say some other thread is holding the GIL by this point, then this thread will have to block there until it gets a chance to lock the global interpreter lock again. But one way or another, by the time it gets down here, it's holding the lock, and so it can do Python-y things again. Like, if there was an error, it can call py-error-setString, which is the way to raise a Python exception from C. Or, if everything went okay, then it returns none. And if this C function returns none, then it pops back out here, and because it's holding the GIL, it can run the rest of the Python on this thread and finish up. So that's why we're able to see these 2 threads sharing the GIL while they're doing cooperative multitasking like network operations. But what about preemptive? I'm going to show you another little Python program here which will not do any socket stuff, so it will never deliberately drop the global interpreter lock. We're just going to do pure calculation. I'm going to do a big loop on 2 threads at the same time, and we'll see whether these threads share the GIL or not. So that's over here. Now, I don't need socket anymore, so I just import threading. And my calculation-heavy function here is called run. And it has an outer loop that goes 500 times. In every outer iteration, it also does an inner loop 500 times. And every time it finishes one of the outer iterations, it'll print its name. Or rather, it'll append its name to the list of messages. Besides that, the rest of the code is pretty much the same. We're going to start 2 threads. Their arguments will be their names, 0 and 1. We wait for them both to finish, and then we print out the messages that they wrote. The question here is going to be, are we going to see just the first thread write 000 until it's done, and then the other thread write 111 until it's done? Or are they going to be able to share the GIL like well-trained toddlers? All right, so there's a lot of output. Let's kind of scroll up to the top here. All right, so we see thread 0 runs for a bunch of iterations, and then thread 1 runs for a bunch of iterations as well, and then 0, and then 1. So they're able to somehow trade off the GIL, even though they're never calling any socket operations that would voluntarily drop it. How is this actually implemented in the interpreter? In order to find that code, we're going to have to go back to that file, ceval.c, that is the kind of the like beating heart of the interpreter, the place that it actually executes bytecode. And let's actually take a step back here for a second. Your Python code is executed kind of in 2 phases. The Python text that you type is first compiled into bytecode, which is a simple binary list of very simple primitive instructions. And then that bytecode is interpreted by the interpreter, which kind of executes like a little virtual machine that executes those instructions one after another. And that stuff, that's over in ceval.c. And the place that we're going to look for where preemptive multitasking is implemented is down here, where Guido has nicely signposted us that this is the interpreter main loop. And the interpreter main loop is a function with this beautiful title, PyEval framex. And we can read it. We can actually understand to some extent what we're looking at. So it takes a frame object that contains all of the code that it's going to execute, and it kind of creates a little virtual machine here with things like a stack pointer and a pointer to the next instruction it's going to execute. We can scroll down a little bit. I don't really know what all of this stuff is about, to be honest. But things get sort of interesting over here. Who here has used a debugger like GDB or like PyCharm? Good, almost all of you, great. If you haven't, that is absolutely the next thing you should do to level up your skills. And debuggers are sort of magical. They can hit breakpoints whenever you tell them to. This is how they actually work. They register a thing called a trace function, which is a callback that the interpreter executes every time it starts a function call. And this is where it tells the debugger, I've started a function call. If you need to do anything in this moment, here's your opportunity. Similar with profilers like cprofile or Yappy, they register callbacks also. And that's how they know when a function call begins and ends, is this profile func. So that's kind of cool. We're looking at the heart of the interpreter, and we sort of understand what we're looking at, but we haven't found what we're really searching for yet, which is where does the interpreter grab the GIL preemptively from a thread that's been holding the GIL for too long? So let's keep looking. All right, there's like a bunch of setup here. There appear to be in-jokes that I don't get. Why equals why not? And then this is interesting, right? Whenever you see an infinite loop, you should probably stop and think. This is where this function executes your bytecodes, one after another, until one of them either returns from this function or throws an exception. And right at the top here, Guido says, do periodic things. Doing this every time through the loop would add too much overhead, so we do it only every nth instruction. And n here is 1,000 by default. That's the check interval. So now the code does just what Guido said it would, which is it decrements some ticker, and if it goes below 0, then it resets the ticker to 1,000. And then, look at this. Give another thread a chance. The interpreter releases the lock. The thread has no control over this, right? Your Python code didn't agree to drop the lock. The interpreter took it, and other threads can run now. And this thread immediately tries to get the lock back. So if there's competition for the GIL, then you'll block here for a while, waiting for some other thread to drop the GIL and for this thread to have a chance to grab it back. If this is a single-threaded program, or if all of the other threads are asleep or awaiting I/O, then all that will happen is every 1,000 bytecodes, your thread will just drop the GIL and reacquire it immediately. So it's a very quick check here. So now we've seen it. We saw where cooperative and preemptive multitasking are actually implemented. Is it time yet to start using what we've learned to write fast code? First, actually, let me ask the question, why does Python have multitasking at all? Like, if it can't really run two threads in parallel at the same time, then why does it have cooperative and preemptive multitasking? The purpose of cooperative multitasking is to finish jobs faster, if those jobs are primarily awaiting I/O. The purpose of preemptive multitasking is not to go faster. The purpose of preemptive multitasking is to simulate parallelism. So instead of one thread running all the way to the end, instead many threads appear to run in parallel, but slowly, all right? But this kind of raises the question of what about safety, right? If you have a global interpreter lock, do you need to worry about thread safety in Python? Like, in a language like Java or C that's completely free-threaded, there's a basic principle that if multiple threads could read or write the same data at the same time, then that's bad. That can cause race conditions. And so you should prevent that with locks, right? The basic principle is that you should lock around access to shared mutable state. I think that we'd better figure out whether this principle applies to Python too, because going fast is great, but going fast and being unsafe can lead to unfortunate consequences. Let's take a look at a program that's going to test this for us. I'm just going to set some global variable n to 0 and try to increment it by 1 with 1,000 threads at the same time. And if the correct output of 1,000 is what we get, then we're probably thread safe. So let's try the experiment. All right, we're going to import threading and sys. And remember that the default check interval in Python 2 is every 1,000 bytecodes. I'm going to turn the knob down to 1. This is going to slow my code down, and it allows a thread to lose the GIL at any moment, and it makes race conditions much easier to manifest. Then I create global variable n equals 0. Foo here is going to increment it by 1. And we're going to do this in 1,000 threads simultaneously. And once all have finished, we'll print out the results. So the question is, are we going to get 1,000 every time, or is something going to go wrong here? Huh. Let's try it again. All right, sometimes 1,000, sometimes 999, sometimes 998. What is going wrong here? We can actually see what the problem is with this function foo by disassembling it. We can use the Python standard library's dis module to disassemble it and see the bytecode that it compiles to. So let's simplify this program down so it's just foo. We'll import dis, and we'll print the disassembly that this function compiles to. And dis makes this rather nice printout here. And we can see that even though foo really only has one line of actual code, it compiles to 6 bytecodes. These first 4, this is the implementation of n plus equals 1. First, you load the value of the global variable n, and that's the first thing on the stack. And then you load 1 also onto the stack. You add the 2 things that are at the top of the stack right now, and then you store the result to a global variable. And then the final two are just loading none onto the stack and then returning that as well. Every Python function has a return statement. If you don't write it yourself, the compiler will insert it. So that's what that is. The important thing is that that one line, n plus equals 1, compiles to 4 bytecodes. And that gives us 3 possibilities to be interrupted. So you can kind of see how this would go wrong. If one thread loads the global value of n as, let's say, 0, it's the first one that started, and then it adds 1 to it, and right before it's about to store that result 1 back to the global value, another thread starts up and interrupts it. Also loads 0 as the global value of n, also adds 1 to it, stores its result, 1, back to the global value, and finishes. And then the first thread we were talking about also stores 1 to the global value. So now 2 threads have completed incrementing n by 1, but the result is only 1. And if that happens a couple of times, you'll end up with this result of 998 when you're expecting 1,000. So that means that the same principle applies even in Python, even with the global interpreter lock, that you have to lock around shared mutable state. So let's do this. Here's the code before, the unsafe code, and then here's after, right? Before, after. All we have to do is create a global lock of our own, right? Nothing to do with the global interpreter lock. And then before we increment n, acquire it, and after we're done, we release it. And if we run this a couple of times, ta-da! It's 1,000 every time. So it's smooth sailing from this point forward. And we can finally talk about what you really came here for, which is how to make code go fast. There's 2 kinds of jobs that benefit from multitasking, and they're called concurrency and parallelism. Now, I want us all to admit something to each other. This is, a small group of friends. Concurrency and parallelism are the same word. If you look it up in an English dictionary, they're going to have the same definition. But among computer scientists, we make this very sharp distinction that concurrency is when a job finishes faster by waiting for multiple I/O operations at the same time. And parallelism is when a job finishes faster when multiple threads do things at the same time. People often use a sort of a cooking analogy for this, that if I put potatoes in the microwave and while they're cooking, I also start some water on the stove, I'm waiting for multiple things at the same time. That's concurrency. If I'm doing multiple things at the same time, like whisking eggs with one hand while flipping pancakes with the other, which I think probably only Adrian could actually do, that's parallelism. And Python threads can't do that. So we're going to finish with 2 code examples. One of them is going to show how to use threads to make a concurrent task go faster. And then the other one is going to show you how you can accomplish parallelism despite the GIL. So we'll do the concurrency one first. Now, a really kind of classic application of concurrency is when you want to fetch a whole bunch of URLs at the same time, but you don't actually do anything with the results. So almost all of your program's time is spent waiting for I/O, and that's something that threads are really good at. So let's say that I wanted to download the websites of all of the great sponsors who made PyCon possible, like Continuum. Is there anybody from Continuum here? No? Well, great guys. At other talks. Maybe they're idealists. So there's over 100 URLs here, and I want to download them all as fast as I can. So I've written a worker function here that's just going to keep trying to pop a URL off of the list and then fetch it with requests, and then it's not going to do anything with it at all. It'll just print that it's downloaded it. We'll write down the start time. Let's start with 10 threads. Let's see how well that performs. And once they've all finished, we'll print out how long that took. So let's see how this goes. It says 101 URLs. And the good news is that the conference Wi-Fi is working at all. But the bad news is that I'm bored. Okay, so that took 16.25 seconds, and the question is, can we make this go faster despite the global interpreter lock by adding more threads? So let's just go straight for the win. Let's go to 100 threads. So we are practically downloading all of them simultaneously. Let's see how that performs. So 16.25 seconds before. Well, that looks better. Ooh. And we got down to something like an eighth of the runtime by multiplying the number of threads by 10. So it's not perfect scaling, but it's really darn good. And this is the kind of thing that you need to keep in mind, that if your problem is concurrency, then a good answer in Python is threads. But what about the other one? What about parallelism? What if you actually need to do multiple things at the same time? For that, we're going to need processes. So a thread is a independent sort of sequence of instructions executed within one process. So threads share memory. It means that they can share information by like updating global variables and so on. Processes, on the other hand, are completely distinct. They do not share any memory at all. And this means that multiple Python processes have independent global interpreter locks, and they can actually run simultaneously. On a multi-core laptop like this one, you can run a dozen of them and take advantage of the multiple cores. But since they don't share anything at all, communicating among processes is much more complex than among threads. So that's the final code example we're going to see, is how do we fork off a bunch of child processes and then use things called pipes to communicate among them. All right. So the task that I've set up here is sort of deliberately dumb. I want to take 10 million numbers and sum them, and for simplicity, all of the numbers are going to be 1. So the sum obviously ought to be 10 million, and we're going to see if we can speed up this by doing it on more processes at the same time. So let's just begin by saying that we're only going to use one child. Now we'll write down the start time, and now we're going to start chunking this list of 10 million numbers into a chunk per child. So at first, we're only going to have one child. So let's create the chunk. It's a list of ones that's 10 million elements long. And now we need to prepare to communicate with the child. And this is much more complex than with threads. We need to create a thing called a pipe. And when we call pipe, we get two ends of the pipe, a read end and a write end. These are two file descriptors. And then we call fork, which is probably the most mind-blowing of all functions, because it clones the current process and then it returns in both the parent and the child simultaneously. It's kind of like if you went to sleep knowing you were going to be cloned in your sleep, and then you wake up in your bedroom and you don't know if you're the original. Everything looks the same. The only way for this process to know whether it's the original or the child is the return value of fork. So if fork returns to the parent, then the parent gets the child's process ID. And so it knows it's the original, and all it needs to do is store away the read end of the pipe that it made. It's going to receive a subtotal from the child once the child's done. And then the parent just keeps looping, forking off children one per chunk until it's done. Now the child, on the other hand, it knows it's the child because fork in the child returns 0. And so the child's job is going to be to sum up its chunk of numbers. So it does that here, sort of intentionally stupidly. And then it's going to print that subtotal, and then it needs to write the subtotal to the parent. So it does that by, you can only write bytes to pipes, so you can't just send the number there. You need to stringify it, encode it as bytes, and then write it to the pipe, and then the child's life is over and it exits. The parent, meanwhile, it gets down here after it's started all of the child processes. And so its job is to read those numbers off the read ends of the pipes. So it does the reverse. It needs to decode the bytes and turn them back into integers and then sum them up to a grand total. Finally, it prints out the grand total and how long it took. So with just one child process, let's see how long this one takes. All right, computers are fast these days. I can sum 10 million ones in 1.2 seconds. And now, what about parallelism? What if we go to 10 children instead? We were 1.2 seconds before, and now, 0.4 seconds. So multiplying the number of processes by 10 let us finish in, what is that, about 3 times as fast. Each of the children summed up its chunk more or less in parallel with all of the other ones because it has an independent global lock. And then the parent could wait at the end and sum them all up. And that's it. You've grokked the GIL. The principle that you just learned is also short enough probably to write on the back of your hand, which is that you can use threads for concurrency and processes for parallelism. And so if you've got 2 hands, you can learn everything you need to know about Python multithreading. On one of them, you write the effect of the GIL on your code. One thread runs Python while n others sleep or await I/O. And then on your other hand, you can write the new thing you just learned, which is that you can make your code go faster by using threads for concurrency and processes for parallelism. Now, if you want to read like an article form of this talk, you could go to bit.ly/grokthegil, and that will show you all of these code examples and let you go through this at your own pace. It includes the 2 principles I described. Beyond these 2 principles, though, here's what I really want you to take out of this talk, which is that be curious. If there's something you want to know about how Python works, you can open up the interpreter code, read it for yourself, and sort of understand what you're looking at. You can find out how Python works by reading the CPython source code. That's what I did, and it made me a better Python programmer. Thank you very much. Thanks.
All right, thanks everyone. We're breaking for lunch now.
Who here has seen the global interpreter lock? So almost everybody here is in the same position that I was in then. Let's be curious. Let's look at it. So I've got Python 2.7 checked out of GitHub here in my editor. I'm using Python 2 rather than 3 because the code that we want to look at is simpler in Python 2, but everything that we're going to talk about today will be equally applicable to Python 3. Let's go find the GIL. It's going to be in a file called ceval.c. And what this file contains is all of the logic that's at the core of the interpreter, where it actually... I'd been programming Python for a number of years and kind of thought that I understood how multitasking worked. I understood how it worked in Java and C, and I kind of lazily expected that the same principles were applicable to Python. I didn't really understand how multi-threading worked in Python particularly until I started working for MongoDB. And once I got there, we were writing the kind of complicated, high-performance Python that required me to really understand how multi-threaded Python specifically works. And in order to do that, I finally really had to understand the GIL. So who here has heard of the global interpreter lock? Please. Yeah.
All right, everyone, we're going to get started. I'd like to introduce A. Jiryu Davis. We are going to grok the GIL.